Okay, welcome back. We're gonna go at least from number 6, and we'll see how long it takes us to go through. If you're doing this, we're doing this is math probability assignment number 2 that's due February 25th. Again, it's very similar to the new one that he gave for us to practice with. And we left off on, we finished 5 on the last video, so we're gonna start on number 6. If you already have these, just skip over to the ones that you are working on if you need any help. But okay, so after a mayor announced his plans to cut budget costs in late 2011, the Forum Research polled 181 people to measure the mayor's popularity. Everyone polled expressed their either approval or disapproval. These are the results. These are the results their poll produced. In early 2011, 56% of the population approved of the mayor's actions in office. In the mid-2011, 52% of the population approved his actions. In the late 2011, the percentage of popular approval was measured at 41%. Okay, so this is the beginning of 2011, middle, and this is the late. What is the sample size for this study? Well, the sample size is how many people did they poll, and we know that that's 1,081. So that's easy. Okay, so part B. What proportion of the poll disapproved of the mayor according to the results from the late 2011? Okay, well, how many of them didn't approve? Well, you have to look at how many of them did approve in the late 2011. So in the late 2011, the percentage of people who approved was measured by 41%. Okay, so we got 41% that did approve. Okay, if we're going off of 100%, how many people disapprove then? Well, if you minus that, right, then we know it's 59%. Oh, my thing keeps going in and out. Okay, so 59%. If you had turned it to a decimal, right, it'd be 0.49, which would come out to 0.59. Okay, so basically 0.59 for me. Again, I don't know what yours says for your because mine says 41%. Yours might say something else. But basically, just remember, minus it from 100, you're going to get the amount of people who disapproved. How many people polled responded that they approved of the mayor in late 2011? So how many people, it doesn't say like what's the percentage, it says how many people. Well, if you're going to get the amount of people, you have to times that percentage from the late 2011 by the amount of people. Okay, so this is again on C where we're looking at, right? Okay, so we've got 41% that said that they approved in the late, right? 41% in the late 2011 that approved. How many people is that? Well, you have to times that by the 1,081 people that were polled. Again, mine says 1,081. Yours might have a totally different number, but it's the same formula. Okay, so I'm going to turn this into a decimal. 0.41 times 1,081. For me, that comes out to 444 people. It will be different for you, but because our numbers are different. But so for C, minus 444. But just so you can see how it's done. Okay, what is the probability that a person supported the mayor based on the data collected in mid-2011? Okay, the probability in mid-2011, it didn't say how many people, it just said the probability. Well, we've got 52%, so it's 0.52. What is the probability that a person supported the mayor based on the data collected in early 2011? In early 2011, it's 56%. So it's 0.56. Again, your numbers, these red numbers change on all of our homework. So I'm just pointing to you where I'm looking so you can figure out where yours is. Okay, number 7, the casino game roulette allows the gambler to bet on the probability of a ball which spins in the roulette wheel, landing on a particular color, number, or range of numbers. The table used to place bets contains 38 numbers, and each number is assigned to a color and the range. Let's start with this. List the sample space of the 38 possible outcomes in roulette. Okay, here are the possible outcomes. We've got 0 and 0, 0, and then we have 1 all the way to 36. Okay, so that's 36 numbers, 1 to 36, and then we got 0 and 0, 0. Those are all options. Okay, so the sample space is 0, 0, 0, 1, 2, 3, and then it'd be 4, 5, 6, 7, all the way to 36. Okay, so then we've got you bet on red. Find the probability of red. Okay, so how many red are there? If you were to count each red, 1, 2, 3, 4, 5, but you don't need to because you know there's 36 and it's every other one, so you know you could divide that by 2 and it's 18. Okay, so we've got 18 over 38. I don't know if he wants us to break it down to the simplest form. Somebody else from his other class says that yes, he does. So next time I'll try breaking it down, dividing that, until we come to the lowest terms. Part C. You bet on the first 12 or the first dozen. So what's the probability? The first 12. Well, you only have 12 in the first 12, right? This first dozen, there's only 12 in this space. So it's 12 out of how many? Not 36. It's 12 out of the 38 because we add these two. So 12 out of 38. Again, I'll probably try break it down to the lowest terms. You bet on an even number. Well, we know even numbers just like the red and black is every other number. And if we take 36 numbers, it'd be 18 over 38. All the even numbers, 36 divided by 2 would be 18. Okay. Is getting an odd number the complement of getting an even number? Why? The answer is no. The sample space includes the numbers 1 to 36, but also 0 and 0, 0. So it's not going to just be an opposite, right? Find two mutually exclusive events, two events that cannot happen at the exact same time. Well, black and red can't happen at the same time, and even and odd cannot happen at the same time. Are the events even and the first dozen independent? Events even and first dozen are not independent because even numbers occur within the first dozen. Okay, so they could, if you hit one, it does take away from the other option, and so they are not independent. If they don't have the exact same amount of options, then they are independent, but they're not. Okay. I don't even know if that makes sense. Alright, again, we're looking at another roulette table. Compute the probability of winning if you bet on two lines of numbers that touch each other on the table. 1, 2, 3, 4, 5, 6. How many times can 6 occur? 1, 2, 3, 4, 5, 6. Okay, we got this 6. That's 1. Then we got this 6. That's 2. Then we got this 6, that's 3. Then we got this 6, that's 4. Then we got this 6, that's 5. Then we got this 6, and that's 7, right? Okay, 1, 2, okay, wait, hold on. Wait, 6 maybe. 1, 2, 3, 4, 5, 6. Sorry, 6, that's 6. So it'd be 6 over 38. Break that down. And we've got 3 over 2, that'd be 19. Okay, so that's broken down in the lowest terms, which I think he wanted us to do. So we got 3 over 19. Compute the probability of winning if you bet on 3 numbers in a line, as in 1, 2, 3. Okay, you're betting on just those 3. So just on any 3, whatever you chose. It'd be 3 out of the whole thing, which is 38. Okay, then compute the probability of winning if you bet on 1 number. So if you only have one thing on 1 number, you only have 1 chance of the 38. Compute the probability of winning if you bet on 4 numbers that touch each other to form a square, as in 10, 11, 13, and 14. 10, 11, 13, 14. So if you're only touching 4, you only have the 4 out of 38 as an option, right? 4 out of 38. That would be correct. Or if we broke this down, we got 2 over 19. Let's see. Okay. So I put 2 out of 19 for part D. Part E. Compute the probability of winning if you bet on two numbers that touch each other on the table, as in 10 and 11 or 10 and 13. Again, you only have 2. So it'd be 2 over 38. Reduced fraction would be 1 over 19. Compute the probability of winning if you bet 0, 0, 0, 0, 1, 2, or 3. How many numbers we have? 1, 2, 3, 4, 5. So it'd be 5 over the total outcome, which would be 38. 5 over 38. Can't break that down anymore. Compute the probability of winning if you bet on 0, 1, and 2. Again, there's 3 numbers, so it'd be 3 over 38. That's the lowest terms. Okay, one more. Let's try to get number 9 in there. An experiment consists of tossing a nickel, a dime, and a quarter. Of interest is the side the coin lands on. H for heads, T for tails. So what are the possible outcomes? Well, we could get 3 heads. We could get 3 tails. We could get 2 heads and a tail. We could get a head, tail, and a head. Or if we were to basically flip this, we got tail, tail, heads, tail, heads, tail. We got heads, tail, tail. Or we got tail, heads, heads. Right? So we've got 8 total things that we could come up with by just flipping those 2 coins. Let A be the event that there are at least 2 tails. Find the probability of A. Well, let's take a look. This one has 2 tails, that's 1. This one doesn't, this one doesn't. This one does, that's number 2. This one does, there's 2 T's here, that's 3. And this one does, that's 4. And this one doesn't. Okay, so it's 4 out of 8 chances. Because 1, 2, 3, 4, 5, 6, 7, 8. There's 8 chances. 4 over 8. If you break that down, it'd be 1 over 2. Okay. Let A be the event that there are at least 2 tails. Let B be the event that the first and second tosses land on heads. Are the events A and B mutually exclusive? Explain your answer. So we put events A and B are mutually exclusive. They are. Having 2 coins land heads up cannot occur when at least 2 coins must be tails. Okay, because there's only 3 coins. There's not 4, right? So you only have those 3 chances. And it already said the first and second had already landed on heads. So it couldn't ever be that. Okay. Okay, yeah, so it's correct. There are only 3 coins, so these events can't occur at the same time. Number 10. Let the probability of C be 0.2, let the probability of D be 0.3, and let the probability of C given D equal 0.4. So we're going to get into some fun stuff again. Again, we're back at that probability of C and D, and we're basically doing the same thing as we did before. I've kind of already gotten the idea that if we're going to look at the probability of C and D, then we need to really be writing a problem more of like C given D, and then finding that top thing. Yeah, so we've got the probability of C and D. That's our outcome. But to get that, we're going to need to do the other with the information that we were already given, right? As long as we're given something that says given, then that helps, because then we can, and if we have the one of the letters, right, then we're going to be able to figure out what C and D is. Okay, so this is what we're wanting here, but this is the formula we're going to need to use, because we have the clue for that, but we don't have this. Okay, and again, what goes underneath? The second letter. Whatever the second letter is, that's what goes under. Okay, we have this. The C given D is 0.4. So we're going to say 0.4 equals, do we have this? No, we don't. We don't have that. But we have this, D. Where is D? 0.3. Okay, 0.3. So we'll go probably C and D. Again, how do we get this here by itself? We have to do the opposite. It's a division problem, so we have to multiply both sides to get it to go away. So we'll cross that out, and we'll cross that out, and we've got 0.12 equals the probability of C and D. This would be the correct answer. Okay, and then, so I've got 0.12. Again, your numbers are going to be different, but you just have to remember, you got to take that probability of C and D, whatever that number is, and then the D underneath, times those two together, you're going to find out what this is. Are C and D mutually exclusive? C and D are not mutually exclusive because C and D do not equal 0. See, when you see C and D, does that equal 0? No. So they're not mutually exclusive because it would have to equal 0 to be mutually exclusive when you times them together. Are C and D independent events? The events are not independent because C given D does not equal to C, the probability of C. Okay. Find the probability of D given C. All right, let's go into that. D given C. Probability of D given C would be, we know it would be the probability of D and C over what? Over C, because it's the second, right? Okay, so do we know what this is? No, we never were given that. It is not the same as C given D. That does not work that way. This is D given C. But do we know what D and C is? Now that doesn't matter what order it's in, right? It doesn't matter that it says C and D, because you're timesing those two together. It's going to have the same exact answer. So whether it says D and C or C and D is exactly the same. So we know the answers for me is 0.12. Whatever yours is in that box, that's what you're going to use. Okay, so I'm going to go 0.12. And over my C, what is my C that I found earlier? Or the C that was given? Mine is 0.2. Okay. All right, let's go. I'm going to just write D/C. All right, so I can figure this out. 0.2 or 0.12 divided by 0.2. Let's get this. Point 12 divided by 0.2 is 0.6. Okay, equals 0.6. Okay, so the probability of D given C is going to be 0.6. And that, for me, that's 0.6. Again, take your numbers. Do exactly the same thing I'm doing, even if it's different numbers. I'm pointing to you which numbers I'm choosing from, and you plug them in for yourself. This is just the basic idea of how you do it. So mine was 0.6, yeah? Okay, so I'm going to stop here. That was up to 10. Question 10.